Video lecture 16F, Acid-Base Titration Curves. In General Chemistry 1, you learned a technique for determining the amount of an unknown substance in solution. This technique was known as a titration. In titration, we use reactions to determine the amount of the unknown in your solution. One common reaction to use is an acid-base reaction. The idea behind a titration is that you can add a known volume of a known concentration to react with your unknown, thereby using stoichiometry to back calculate the amount of unknown in the solution. We usually use acid-base indicators to determine when our reaction is complete. But one very useful technique is to use pH. Using a pH electrode and meter, we can monitor the pH as the titration commences. Usually this results in a plot known as a pH titration curve. This titration curve is sinusoidal or S-shaped, and the equivalence point exists at the inflection point of the plot. Even though monitor the pH of an acid-base titration is very useful, you still can use an indicator to help you determine to give you a nice visual of the endpoint of your titration, which occurs at least one point beyond the equivalence point. The shape of your titration curve will depend on the nature of the titration that you are doing, and whether or not the acid or base or base are strong or weak. Pictured here is a titration curve for a strong acid being titrated with a strong base. There are a couple of features to point out in this titration curve. If you look before the inflection point or before the equivalence point, you'll notice that the pH is very low before the equivalence point of the titration. This is because when we're adding strong base to a strong acid, the base will completely react with the acid in the solution, leaving only acid present. This means that H3O+ is in excess during most of the titration before the equivalence point. This means that the pH will be relatively low. Another important thing to note is where the equivalence point occurs. Note that in this plot, the inflection point occurs right around pH 7. This makes a lot of sense. When you've completely reacted all of the HCl with all of the NaOH, you'll be left with sodium chloride and water in solution. Sodium chloride contains a counterion of a strong base, the sodium ion, and the conjugate base of the strong acid HCl. This means NaCl is a weak salt, and the pH of the solution will be right around neutral. When we choose our indicator, we want something that will change color right around the equivalence point. There are two very nice indicators for this purpose. The first is bromocresol green, which changes color from yellow to blue right between a pH of 4 and 6. This could be useful in figuring out the endpoint of the titration, since you'll stop right before reaching the equivalence point. Another useful indicator and common indicator is phenolphthalein. Phenolphthalein changes color between 8 and 10. Therefore, you'll be able to detect the exact moment after you've reached the equivalence point. Calculations involving the titration of strong acids and strong bases are very easy to do. The most difficult part is to use stoichiometry to determine what is left over after the reaction. In this example, we'll determine the pH of a solution that is formed when we mix 600 milliliters of 0.1 molar NaOH with 400 milliliters of nitric acid. The concentration of the nitric acid is 0.70 molar. The first thing to remember in this calculation is that reactions involving strong acids or strong bases will have very large K values, meaning that this reaction will occur to completion, using up all of the limiting reactant. This means that if we want to use an ICE table to help us to solve this problem, the X value, or extent of reaction variable, will be determined by the amount of limiting reagent we have. In order to keep things very simple, we will work in moles. We first start by determining the moles of nitric acid and NaOH in solution. We can calculate this by multiplying the volume of the solution times the molarity of each solution. Note that we have to convert milliliters into liters in order to cancel out the liters in the molarity. This gives us 0.28 moles of nitric acid and 0.006 moles of NaOH. Now we need to set up our ICE table, but first we need a balanced equation. The reaction between nitric acid and NaOH will produce NaNO3 and H2O. Note that to figure out the products of this reaction, we can do a double displacement, swapping the cations and anions of the reactants. To set up our ICE table, we start by putting in the initial moles of our reactants, nitric acid and NaOH. We note that sodium nitrate will start with a concentration of 0. When the solutions are mixed, the HNO3 will react with the NaOH. And since we have a smaller number of moles of NaOH, all of the NaOH will be consumed. It is the limiting reactant. And since the stoichiometry of a reaction is all 1-to-1, this will also be our change value. The amount of HNO3 in solution will decrease by 0.006 moles, and the amount of NaNO3 in solution will increase by 0.006 moles. So that at equilibrium, we end up with no more NaOH, 0.0060 moles of NaNO3, and 0.22 moles of HNO3. Note that NaNO3 is a neutral salt. This means that it will not at all affect the pH of the solution. We're now ready to calculate our pH, but we first need a hydronium ion concentration. To get this, we take the moles of HNO3 that will remain after the reaction and divide it by the total solution volume, which so happens to be 1 liter. This means that we end up with a 0.22 molar solution of H3O+, and taking the negative log of that value, we end up with a pH of 0.66, a very low pH. This is very common with reactions that involve titrating a base or an acid with weak base. A strong acid with strong base. Now let's take a look at what happens when a weak acid or a weak base is introduced. Here's a titration curve for the titration of acetic acid with NaOH. Notice that the pH before the equivalence point is much higher. This is mainly because acetic acid is a weak acid and will have a higher pH than a strong acid. But also look at the beginning of the titration. The pH in one region remains roughly constant. This is because as you react the NaOH with acetic acid, you're also going to form the acetate ion. And since the acetate ion will be in solution with the acetic acid, you're going to form a buffer. This is going to keep the pH pretty constant until you start to run out of acetic acid. Then the pH will begin to change very rapidly. Another noticeable difference is that at the equivalence point, the pH is higher than 7. In this case, roughly around 8.5. Meaning that at the equivalence point, the reaction mixture will end up being basic. This is because the sodium acetate product is a weakly basic salt. The acetate ion will undergo hydrolysis to form a small amount of hydroxide ion, which will cause the pH of the solution at the equivalence point to be weakly basic. Let's take a look at our indicators again. For this reaction, bromocresol green isn't a very good indicator for our titration because its pH color change range is well below the equivalence point pH. However, bromocresol green can be used to study the buffer region, which you will do in a later lab. However, our other common indicator, phenolphthalein, is perfect for detecting the endpoint in a weak strong titration, a weak acid strong base titration, since it changes color between the pH range of 8 and 10, which is where the equivalent point will likely be for these types of titrations. So phenolphthalein would be chosen over bromocresol green to detect the endpoint of the titration. Another titration that we can look at is titrating a weak base with a strong acid. Notice that this titration curve is the mirror image of our previous titration curve. Here we are titrating ammonia with HCl. Notice that the buffer region is at a relatively high pH this time, and that the equivalence point is weakly acidic. This is because ammonium chloride is a weakly acidic salt due to the hydrolysis of the ammonium ion. In this type of titration, you could use bromocresol green to detect the equivalence point, but you can also use another indicator, methyl red, which changes color in about the same region.